So I'm going to talk about how weighted model counting is used for Bayesian network probabilistic inference and how that interaction could be improved. So more generally, we have this problem of computing some probability from some representation of a probability distribution. This could be a graphical model such as a Bayesian network or a Markov random field, or probabilistic programming language. In any case, we can use weighted model counting as the mechanism for computing some probability. Weighted model counting is an extension of propositional model counting that adds weights to literals. So in this example, we have two variables, so we have 4 weights on 4 literals, and the goal of WMC is to calculate the sum of the weights of the models of some formula. So this example formula has 3 models, and the weight of each model is product of the weights of all literals in it. This computational framework has applications mostly for probabilistic inference, but also more recently in neural symbolic artificial intelligence. So that was the classical way of conceptualizing WMC. Alternatively, we could look at it from the perspective of Boolean algebras and measures. We could consider this Boolean algebra that contains all equivalence classes of formulas definable using the variables in this set. And then we have this simple definition of a measure, where a measure is a non-negative function that is 0 on the bottom element and is additive whenever the two elements contradict each other. And then we can notice that WMC can also be thought of as the process of calculating the value of the measure on some element of a Boolean algebra. And so the algorithmic emphasis shifts towards a convenient representation of the measure. So in the paper we describe a type of measures called factorable measures that can be thought of as a collection of mutually independent random variables, and we show that WMC, the way it is typically defined, is only able to evaluate these factorable measures. The way this limitation is usually addressed is by adding more variables, and we show that this is indeed always possible. It's always possible to take any probability distribution and keep adding variables to turn it into something that classical WMC can handle. Even though it's always possible, it's not necessarily a good idea, especially if the WMC algorithm supports some more expressive way of reasoning with weights. So going back to Bayesian networks, we can construct a representation of a conditional probability table by combining these simple indicator functions using some operations, most of which are defined pointwise. And we can represent each CPT in the network as a function. And this has been done before to some extent. Combining this type of encoding with a recently proposed WMC algorithm, ADDMC, gives us the following results. So the first thing we can notice is that ADDMC with all the other encodings is not doing that well on Bayesian networks, but with our encoding its performance becomes quite comparable to that of other algorithms. And if we compare the performance of our encoding with ADDMC with the state of the art, we can notice many instances that were unsolved by the state-of-the-art approach that are solved by our approach, and many instances that were slow, quite a bit slower with the state-of-the-art than it is with ours. Especially from these two datasets. So that raises an interesting question: what makes these datasets more suitable for our encoding than for any other encoding? To summarize, we showed that WMC, with its classical standard definition, can represent and compute any probability from any probability distribution if we just keep adding variables. But this is not the right approach for WMC algorithms that support some more expressive ways of reasoning about weights. And specifically with ADDMC, we were able to get more than 2 orders of magnitude improvement in inference speed just by avoiding these redundancies, redundant variables and clauses. The encoding we proposed can still be improved in many ways, for example by transferring ideas from other WMC encodings, or by developing some tricks and gadgets that are specific to our function-based representation that don't apply to propositional logic. And we explore some of this in our SAT paper, where we take encodings and remove the redundancies while still keeping aspects of the encoding that make the encoding good.